Okay, morning everybody. So this is lecture 3 of Introduction to AdS.
Okay, so I'm glad to see that lots of people are awake at 8:30 in the morning. So today I will try to give you a prescription to calculate observables in the AdS CFT correspondence for gauge theories by using the gravitational description or the string theory description. But before I do that, let me spend a very short time making sure that the various metric conventions you've seen yesterday make sense to you. So I'll just quickly illustrate to you how you can visualize AdS space and various coordinate charts you can put on it, which are useful for different purposes. So to be general, I will talk about a d plus 1 dimensional anti-de Sitter space it's nothing but I'll describe the Lorentzian geometry for a moment, and we'll switch back to talking about the Euclidean geometry, which you've seen written down yesterday. All this is a fancy name for a Lorentzian hyperboloid. Okay? And this geometry is described as follows. So you take, I'll describe it to you the way I describe a sphere in flat space, by giving you an embedding of this hyperboloid in something in one higher dimensional space. So I'll give you an embedding in d plus 2 dimensions. But instead of giving you an embedding in d plus 2 dimensional Euclidean space, I'll give you an embedding in a space with slightly strange signature, which has 2 time-like directions and d space-like directions. Okay? So consider our d comma 2 with coordinates x minus 1, x naught, x1 to xd. And this has the standard flat metric, except as I just said, there's some strange sign conventions here. 2 of these directions have negative signature. Okay. So this is the parent geometry. I'm going to describe some surface in this geometry. And all I need to do to describe some surface here is to give you one equation in these coordinates which describes the surface. So the equation is just that of an hyperboloid where r is some fixed constant. Okay? So you can visualize this as saying that here is the hyperboloid embedded in this parent flat space that I'm considering. Now, the nice thing about this is that it makes the symmetries of the AdS space manifest. You saw yesterday in the lecture on by Kostya, that conformal field theories in 4 dimensions have an SO4, 2 symmetry. Anti-de Sitter D plus 1 has a symmetry group which corresponds to, well, if all of these signs were positive, okay, so if it was RD plus 2, then the symmetry group is SOD plus 2. It's just the rotation group in Euclidean space. But here, because 2 of the signs are negative, the symmetry group is SOD, 2, where the 2 refers to the fact that there are 2 time-like directions in this framework. Okay. So the various coordinates one can write down. I'll write coordinates which at first sight will look somewhat different, but make visualizing the geometry a bit easier, and then I'll go back and write coordinates that you've been seeing in the lectures yesterday. So the simplest way to write down coordinates on the hyperboloid is to solve that equation. You have d plus 2 variables, but you want only d plus 1 variables coordinates on the hyperboloid itself. So solve for the extra coordinate up there by explicitly solving for it, and then plug back into the metric to write down the induced metric on the hyperboloid. Okay? So the analogy with you want to keep in mind is the way you get metrics on spheres by thinking of spheres as embedded in flat space. Okay, the simplest way to solve this is to exploit sort of standard trigonometric relations and introduce coordinates rho tau and what I will just schematically call omega as follows. Where you can see by virtue, if the omegas squared sum to 1, then that equation up there is trivially satisfied by this parameterization. Yeah, so when I sum over x1 to xd, I just get r squared sin squared rho, and when I sum of these two guys, the taus disappear by virtue of the same sign between x minus 1 and x naught, and the cosh and sinh can cancel to give you just minus r squared. And in the hyperboloid, the coordinates are these coordinates are as follows. Rho runs out from and tau is the angle around the hyperboloid. And I have just drawn for you what looks like a 2 surface. Every point on the 2 surface has to be supplemented with this sphere which is sitting inside. If I plug this parameterization into my metric, flat metric on Rd, 2, I get a simple metric for the Lorentzian anti-de Sitter space. Okay. Now, should have used a different label, but let me write it like this. So this is the metric you get by plugging this guy in, and what you see is you see a d-1 sphere whose radius is given by sine hyperbolic of rho, and you see a coordinate rho that runs from 0 to infinity, and you see a coordinate tau which has time-like signature. Okay? And this parameterization is a bit misleading because tau, the way I have chosen it, seems to be compact. If tau was compact, then because it's time-like, it looks like the space has closed time-like curves. So what I really want to think of the AdS d plus 1 is to write down this parameterization and then let tau run from minus infinity to infinity. So if you like, start with Minkowski space where you have periodically identified time and then decompactify it so that you don't get any closed time-like curves. So at the end of the day, I want rho taking values in 0 infinity and tau taking values on the real line. And these coordinates are usually referred to as global coordinates on AdS.
According to the lecture on dynamical plasma, compactified time has a very specific.
Okay, so good. So I'm talking here about the Lorentzian AdS spacetime. Okay, so if I switch to the Euclidean space, then I will be talking about periodically identified time as giving me a description of the thermal field theory. You'll also see another coordinate chart that's usually used to refer to the global AdS geometry, where R, of course, is nothing but sine hyperbolic of rho. And this brings me to a point where I can discuss what the global geometry of AdS space looks like. Okay. I'll tell you the answer and then explain it in terms of what we see there. You should really visualize anti-de Sitter space as nothing but a soup can, an open soup can. Where rho, again I'm drawing just a three-dimensional slice. I'm not going to be able to draw it in higher dimensions. Rho is the coordinate that runs from the origin here in the middle of the soup can out. Large values of rho correspond to boundary of the space-time. So the line I've drawn here is rho equals infinity, which is rotated around, and so the boundary of the soup can is the boundary of anti-de Sitter space, and the time t, or tau, as I've denoted here, runs up. A constant tau slice of this geometry is nothing but a Euclidean hyperbolic space. The simplest case to visualize is when D is 2, when you're thinking of AdS 3. So AdS 3 is nothing but this cylinder, which is open at the top and the bottom, time is running up. The interior of the cylinder, rho is a coordinate that runs along inside with origin in the middle and gets to infinity by the time I get up here. So really, this is an infinitely big cylinder. And the way I have drawn it, I have brought infinity to finite distance by conformally compactifying. And sections of this cylinder at any fixed value of time are just what in 2 dimensions are called the Poincare disk. Okay. So we could do much more about this, but I think I'll refer you to the sort of standard literature on how to think about sort of obtaining the Penrose diagram and so on of anti-de Sitter space, and instead try to relate back to the standard coordinate chart that you've seen yesterday in the various lectures. So the coordinates you were seeing yesterday, or the 2 sets of coordinates you were seeing yesterday, are typically referred to as Poincare coordinates, and these you can obtain by the following solution to the embedding equation. I'm going to introduce a new set of coordinates, x vector. X is a vector in d minus 1 dimensions, t, and the last coordinate will be u. Now I'll let you check that this parameterization solves the embedding equation given up there. Okay, so it's a very easy exercise to check this, and if I plug this now into my metric up there, I get the metric that we derive by looking at the near extremal limit, the near horizon limit of the D3 brane, i.e. you get what was this. And now one more change of variables brings me back to the coordinates which are being used by Kostya and Larry in their talks. Now This all seems like a bit of a slightly convoluted exercise in writing coordinates on the same manifold. It just so happens that these are useful for different purposes. So, the coordinates which are sort of good coordinates on the manifold, which cover the entire AdS hyperboloid, are these. These coordinates with this range that I mentioned here are a complete coordinate chart for the manifold. The coordinates given here only cover a fraction of the manifold. So, which fraction do they cover? So, imagine taking the cylinder of anti-de Sitter space, this infinite cylinder that I had up there, and wrapping a handkerchief around it. Okay. So, the handkerchief wraps in a fashion that slices this cylinder in two null planes. It slices into a null plane up and a null plane down. I'm still talking about the Lorentzian spacetime. The region interior to this, bounded by these two null planes in the future and past, is the part of anti-de Sitter space that's covered by these coordinates. If you stare at these coordinates, you see that something special happens at two values of u, or in those coordinates at two values of z. So, here something special happens at z equals 0 and at z equals infinity. If you trace back the relation between, well, I have given you a solution to these x coordinates in terms of various parameterization. So, you can trace back what happens to particular values of z or u in terms of particular values of rhos, taus, and so on. And you will find that z equals 0 here corresponds to going to large rho, i.e., to the boundary of the anti-de Sitter space. Whereas going to large values of z, i.e., z to infinity, corresponds to hitting this plane. So, in these coordinates, as z goes to infinity, the coefficient, the metric function GTT goes to 0. This looks like a horizon of a black hole. If you remember, if you have a Schwarzschild black hole, the metric function GTT goes to 0 as I go towards the horizon of the black hole. This is exactly the same property that's happening to this metric as z goes to 0, but it's nothing special. There is no black hole here. It's just this particularly chosen null hyperplane by my choice of coordinates. It's a completely non-singular part of the geometry which is made special by a poor choice of coordinates. Okay?
When you reconstruct holographically the space-time using this holographic normalization method, you use this epsilon Graham coordinates. So
That's right.
As this set of coordinates.
Yeah.
And using this, you can reproduce the whole space-time.
No, you certainly cannot reproduce the whole spacetime.
How can you?
So the issue with sort of what's done in this holographic renormalization approach is now a question of where do you want the field theory to live. Whether you want your field theory to, so the boundary here as z goes to infinity, as z goes to 0, is just a copy of flat space parameterized by x and t. The boundary in these coordinates as rho goes to infinity, which is the boundary of the real anti-de Sitter space, is a cylinder parameterized by a sphere and tau. So maybe I should write that down. So here whereas here and if I want to work with a conformal field theory on RD in flat space, then I should use the Pfefferman-Graham coordinates. Whereas if I want to work with a conformal field theory on a sphere, I should work with the global coordinates. So whenever people do holographic renormalization, they are specifically referring to working with conformal field theories in a flat background and then doing renormalization group flow there. So for those of you who are wondering what this business of holographic renormalization is, this is the part I'm now going to get into now that I've finished giving you a overview of the various coordinate systems. One last thing I want to say is in both sets of coordinates that I've chosen and that I'll work with, either the global ones or the Poincare ones here, I have a explicit time-like killing field. Here I have d by dt, which is time-like, and here I have d by d tau, which is time-like. And in both cases, I can analytically continue either tau to I tau or t to I t and write down a Euclidean geometry. Okay? So this is the Euclidean geometry that people will work with that you saw yesterday, and I won't sort of write down the explicit metric. All you need to do is flip this sign. Okay. So we have all the pieces in place now for me to start giving you details of how to relate quantities on two sides of the correspondence. And to be specific, I will work with the Poincare coordinates in Euclidean space. Okay. Okay. The first question we want to ask ourselves is the following. N equals 4, as you've heard, super Yang-Mills, is a conformal field theory. Which in particular means that it doesn't, as Laddie explained, have any particle excitations. So what does this mean? So in a conformal field theory, there are no length scales. So there are no massive excitations, because any massive excitation sets a scale given by the mass. In particular, all excitations of this field theory have to be massless, and we know that massless particles mediate long range interactions. So if I wanted to sort of study this field theory in a conventional quantum field theory sense and define S matrices, I would need to be able to define in and out states which I can scatter and talk about an S matrix element. But in order to be able to talk about an S matrix element and define an in and out state, I have to imagine that at very early and very late times I am able to make my particles non-interacting. But this theory has no particles, and whatever massless fields there are interact at arbitrarily long scales. So this theory does not have an S matrix. So what are the natural observables in a conformal field theory? The natural observables actually are nothing but correlation functions of gauge invariant local operators. So what do I mean by this? So apart from being a conformal field theory, this theory is a super Young-Mills theory. In particular, it has local gauge symmetry. So the only kind of objects I can talk about are those which are explicitly gauge invariant. That explains this bit. And what I mean by local operators is as follows. I take my fundamental fields of this theory, which for n equals 4, it's a gauge theory, so there are gauge fields, and these transform in the adjoint of my gauge group, which I will take to be SUN. There are scalars there are 6 scalars where the I runs from 1 to 6. Also, in the adjoint of SUN, and you have seen the bosonic Lagrangian of this theory in Kostya's lecture from a couple of days ago. And there are fermions, but I won't write out what the fermionic content of this theory is. What can I do with these fields? I can take these fields and construct an operator of the following kind. Okay, so I can stick together the scalars, covariant derivatives of scalars, gauge field strengths, and so on, all at the same point, and then make sure it's gauge invariant by taking a trace with respect to the gauge group. This, by construction, it explicitly transforms in the singlet representation of SUN and is gauge invariant. So when I talk about gauge invariant local operators, I mean precisely object of this kind. I take my fundamental fields, string them together, and then make sure they are gauge invariant by taking a trace. And you'll see much more about sort of gauge invariant operators in the field theory and what kinds of operators we would consider. In Kostya's lecture, he will tell you more about them. I will talk primarily about a particularly special class of operators. You've already heard these words yesterday. Called chiral primary operators, which happen to be special from the point of view of representation theory of the superconformal algebra, which is the symmetry algebra of n equals 4. So these are operators of the following form. They are made up only of the scalars, and what I have done here is I have indicated a particular symmetrization here in my notation. I take n scalars, each of them carries an index. There are 6 of them. They transform in the 6th representation of the vector representation of SO6. I string them together and take a symmetric traceless combination of n of these objects. There's the brackets here, these brackets. Refer to the fact that this is a symmetric So this object is a singlet under the gauge group by the trace that's sitting outside, but it transforms in the nth rank symmetric traceless representation of the global symmetry group SO6. So that the 2 traces involved, one which is sort of happening inside has to do with the global symmetry of the theory, and one which I have to explicitly do to make sure that this guy is a singlet of mine, is a gauge invariant operator. And these guys have some given charges and dimensions, and it's these guys that we can describe very nicely from the perspective of the bulk. Okay, so that was the field theory part of what I wanted to say. So we want to be able to calculate the following objects. So we have these operators. Let me give it some label, OI. And what we want to be able to calculate is correlation functions of the following kind. So this is one class of observables that we are going to be interested in. Yes. So all the calculations I will do here will be in the vacuum state of the Young-Mills theory. We could generalize this prescription to do it in general excited states. I'll tell you how to do that once I tell you how to do the calculation in the vacuum. So any questions about the field theory so far?
Is this just an example of a chiral primary, or is it all chiral primaries?
Actually, these are all the chiral primaries of the theory, the symmetric traceless in SO6. So these are all the half BPS states in n equals 4.
Mukund, your index I So I mean, does that? I mean, would that be n or would that be I?
Yeah, it's some particular.
Yeah,
sort
so
of,
I mean,
it's a particular tensor index.
Okay. I mean,
Because it's a symmetric traceless tensor in SO6,
yes.
nth rank tensor. I'm just collectively representing that whole index structure by I. So it's just a shorthand notation for the index notation that goes on. Okay. So in field theory, how would I calculate these kinds of correlation functions? What I would do is I would take my field theory Lagrangian. Suppose I was to do this in perturbation theory. I would take my field theory Lagrangian, add to it the operators that I am interested in with a source term, do the path integral, and take functional derivatives with respect to the source and obtain the correlation functions. You start with, let me write it as a Lagrangian. I start with Lagrangian of n equals 4, which I haven't written down and I won't write down, but it's a well known Lagrangian, plus I add to it the operators OI with some source which I will very conveniently call phi naught, the index I. And I'll put a factor of n here for reasons that have to do with large n scaling. So I consider this Lagrangian, and then I calculate the path integral Okay, now I'm going to get into terrible trouble with my notation. So, okay, let's leave those that way. So phi's here are the scalars of n equals 4, and this phi naught is some external source. Maybe I should just call it J naught. So this, if I evaluate the path integral, is some functional of these let me use a standard notation. I'm going to so this is just some functional. I've integrated over all the field theory, done the path integral over all the field theory variables. I just am left with some functional of the source terms that I stuck in to my Lagrangian. If I take this functional and take variational derivatives with respect to my sources, then I recover my correlation function. So what I want to give you now is a prescription to calculate this generating function of correlation functions from the dual point of view, from the point of view of supergravity on AdS5 cross S5 background. And here I will make my first simplification, which is to get rid of the S5. Okay, so this is the quantity we are after, and we need a prescription to be able to compute this by doing some string theory or gravity calculation in anti-de Sitter space. So far, this discussion has been completely general. You could have done this for any quantum field theory. So really, the way the correspondence was set up yesterday is I had to do string theory on AdS phi cross S5. As various people mentioned, we don't really know how to do string theory fully on AdS phi cross S5. So what we are going to do is do a slightly simpler problem, which is to not worry about all the excited string modes, but only work with gravitational degrees of freedom, supergravity modes on AdS phi cross S5. Okay, so these are the 0 modes. And the string spectrum contains states which are excited string states whose energies will scale like 1 over alpha prime. And those are the states I'm not talking about here. So I want to compute this guy, which of course is what this path integral does compute. So since I'm doing gravity on AdS phi cross S5, I can do the following. S5 is a compact manifold. So I can expand my fields, the gravitational modes on AdS phi cross S5 in terms of eigenfunctions of S5 and do a mode decomposition. And all that buys me is I get extra mass terms coming from higher harmonics of various fields on the S5. So this is nothing but standard Klein reduction, not done on a torus, but done on a phi sphere. Okay, so if you have some 10-dimensional fields schematically, okay. So chi is some 10-dimensional field which is function of y, which are coordinates on AdS, and x, which are coordinates on S5, or let me call them omega, which are coordinates on S5. I just write these as chi bar of y phi. Some by L omega phi, and then figure out what the eigenfunctions, these generalized spherical harmonics on S5 are to induce appropriate mass for these fields chi bar. Okay, so there's nothing sort of very fancy here, but the only thing you need to remember is we don't need to worry about the S5. We can reduce all the fields, all the fluctuations of fields on S5 down to 5 dimensions.
Remember, there's always this issue whether you can truncate the 5-dimensional relation.
Okay, So for the modes I'm discussing it, I'm only discussing linearized fluctuations because I'm going to be looking at only linearized fluctuations about AdS5 cross S5, because that's really what is implicit when I'm calculating sort of correlation functions here. If you want to talk about full solutions, you want to ask whether all solutions to supergravity in 10 dimensions can be described in 5 dimensions, which is one question. The question you are asking is, can all solutions in 5 dimensions be uplifted to 10 dimensions? And I think the answer is yes for AdS5 cross S5. Certainly for other cases, I know there are proofs that you can do this.
No. For general case, it cannot be uplifted.
Sorry?
For general case, it cannot be.
No, so for AdS4 cross S7, all solutions.
S7 is okay, but
yeah.
Sasaki Einstein self-fold, it cannot be.
No. So the question is, are all solutions to gauge supergravity
Yeah.
solutions to type 2B superstring theory in 10 dimensions?
Yeah.
And that I think the answer is yes. So you can change the boundary conditions.
Consistent truncation only holds for S5.
Exactly.
Yeah.
So I'm saying that for S5 case,
Yeah.
I think the answer is yes. Okay, but that's an issue that's slightly distinct from what we're talking about. So let's ignore that. In what follows. Okay. So in order to be able to do this computation, I need to give you a dictionary between operators in the field theory, the operators that I'm interested in, and fields that are propagating in AdS5 cross S5. Okay? So let me first assert what the correspondence is. So given an operator O in the field theory, the source I couple to is the boundary value of some bulk field shall call psi. So every operator in the field theory, there is a field propagating in anti-de Sitter phi space, which has a boundary value which I've called J naught. So what do I mean by this? So psi as z goes to 0 okay, so again I'm working in now in anti-de Sitter space in point correct coordinates z and a 4 vector x. This is a 5-dimensional metric. X vector refers to 4-dimensional R4. Schematically, there is a bulk field psi whose value as z goes to 0 is the value of the source I want to insert on the boundary.
You mean R4 or R3?
So I really mean R4 because I'm going to formulate this whole correspondence in the Euclidean space. So there is a similar story I can say for R3, 1, and I have to be just a bit careful about what I mean by this statement here.
The question of finding the dictionary is a question of group theory, or?
So for these, actually for the chiral primary operators, it is almost a question of group theory. The representation content of fields in AdS5 fall into the same representations as the representation content of operators in n equals 4. So there is a trivial kinematic check. The correspondence works at that level. So to orient you, let me give you what kinds of fields I'm talking about here for the chiral primary operators. But now I'll explicitly talk about what the conformal dimension of the operator is. So I'm going to worry about a chiral primary operator whose conformal dimension is delta, and this corresponds to a massive scalar field propagating in AdS5, and the mass squared is related to the conformal dimension as follows. And this particular scalar field in the case of chiral primaries arises in the 10-dimensional description of AdS5 cross S5 as a particular harmonic of gravitons with polarization along the S5. Okay, there's some I have to do some diagonalization here. So there is you take the 10-dimensional fields with indices only along the S5 so that you get a scalar in AdS5 when you reduce, and particular polarizations of them give you this particular chiral primary operator in 5 dimensions. The field that corresponds to chiral primary operator in 5 dimensions. Okay. So now I'm ready to write down the formula for calculating correlation functions. Again, I'm just going to write this down, and then I will motivate for you how to use it and what to do in general to calculate with it. So the quantity we are interested in was the conformal field theory generating function of correlation function, which was nothing but expectation value of this guy the claim is that this is minus the logarithm of the string theory partition functions such evaluated with the restriction that all fields obey the boundary condition that I'm imposing, that the source I'm interested in to couple to the field, couple to the operator on the boundary is given by the boundary value of some bulk field. So think of this as some sort of standard Dirichlet type problem. I give you some source terms on the boundary, which are just boundary values of some fields propagating in the bulk of anti-de Sitter space. And in the approximation I'm going to work in, this is going to be nothing but the supergravity action evaluated as a function of J naught, where all the supergravity fields obey this boundary condition.
In general, you want to include like a factor of the radial coordinate right in front of the source.
Okay, so I haven't told you anything about regularization yet. I'm giving you a formal prescription, and I'm going to talk about both wave function renormalization and putting in the factors of the radial coordinate in a moment. But formally, this is exactly what I want to do. I want to compute the supergravity action with prescribed boundary conditions. And you're completely right. In order to be able to get finite answers, I need to worry about where I cut off this and what kind of regularization I do.
Sorry. What about the gate choice for both cases?
Sorry?
Gate choice. When we take a path integral for gate theory, we have to choose gate choice. We have to take some gate choice.
No, but the answer is completely gauge invariant.
Yeah, I'm right. In that prescription, how can we relate those two prescriptions, those two gate choices?
So the claim is you pick whatever gauge you want in the bulk, and you calculate with the appropriate boundary conditions, and you should get the same answer irrespective of the gauge choice in the bulk and likewise in the boundary. Okay. So let me write down slightly couple more formal expressions, and then we'll go back and try to evaluate these explicitly for the case of 2 and 3 point functions to see how these things work. But even before that, something that was mentioned yesterday becomes manifest. So let me write down one more expression, and we'll see that. Okay. The bulk field psi is of course a function of the 5-dimensional AdS coordinate, is a function of where I am along z and a function of the x. And like with any standard Dirichlet problem, I'm trying to tell you to solve the equations that this bulk field satisfies in an anti-de Sitter space in terms of its boundary conditions given at a particular point z equals 0 input. And this you can always formally write down as by writing down an integral expression with a kernel where this quantity is referred to as the bulk to boundary propagator. Pictorially, okay. I can describe this if I do the following. You've seen that these coordinates, okay, let me try to be consistent with the pictures you've been seeing. Of anti-de Sitter space of having a boundary at z equals 0 and the z coordinate runs, and I'm suppressing here the x coordinates which sort of run along this way. I'm just drawing one of them. Instead of this picture, let me sort of take this z coordinate and compactify it. Let me draw it as a circle. So that the boundary z equals 0 is the boundary of a disk. Okay. So I insert some operators on the boundary, and it's their correlation function that I want to calculate. So what I'm going to do is, at this point, I have coupled an operator to a source J naught, and what I'm instructed to do by that integral expression is to start with my source and evolve it inward to get me a field in the bulk by this particular bulk to boundary propagator. So schematically, if I want to know the value of the field psi at this position z and some coordinate x, I start here and integrate in by this kernel. So this is a simple prescription for finding the bulk value of the field, but then computing correlation functions can be very simply described in this pictorial language. What do I want to do? This field psi I have some action of the following form. It comes from gravity, so it will have arbitrarily high order interactions. They are arbitrary, not just 2 and 3 point functions, but they are endpoint functions just from gravitational interactions, which are schematically indicated for a single field as follows. So in order to compute this extremum of supergravity, I have to take this action, plug in the solution for psi given the boundary value, and evaluate the action on the solution. But to obtain particular endpoint functions, I could just as well diagrammatically, since I am going to do eventually functional differentiation with respect to the source terms, to obtain not the generating function but the actual correlation functions, that again I can represent diagrammatically in the standard fashion as follows. suppose I want a 2-point function in the boundary. I want to calculate this guy. I couple O1 to source J1 and O2 to source J2, and then I solve the bulk wave equation. Let's say I start here, I find the field, but then I have to connect it back to the other point. So in supergravity language, calculating this guy amounts to calculating a bulk diagram of the following kind. So I haven't still told you how we do this calculation, but schematically it's clear that I sort of evolve the field out from J2, and then I have to make sure it sinks back at J1. Computing higher point functions is just as simple, except now I have to start worrying about higher point interactions in the bulk. So if I want to compute 3-point functions, I have 3 sources. And what I need to do is evolve my field from each of these sources inward, and then intertwine them in the bulk by the rules of this action. So I compute, if I just had a 3-point vertex, I want to compute a 3-point function, I intertwine the field at some point, bulk point Z W, but this bulk point could be anywhere. I have to integrate over the bulk insertion point. Okay, so those are the kinds of calculations we would need to do in supergravity to obtain the correlation functions in the field theory, and tomorrow I'll explicitly show you how to compute 2-point functions and sketch how the 3-point function is calculated. But before I do that, before I stop, let me tell you that already here you see one feature that you can extract without doing any extra calculation, which is if I want to compute the 1-point function of the field, I just need to know its asymptotic boundary value. So any field that sort of goes to the boundary, the value it picks up at the boundary is the 1-point function, is the wave for that operator in the field here. So we'll see this bit more explicitly, and I'll show you how to compute the 2-point function, including the regularizations that are needed tomorrow.
Do you have any quick questions? David.
Just on the 3-point diagram, you wrote O's on the X. Were they supposed to be K's? Or
Oh, yes, sorry. I meant I wanted to compute expectation values of O, but in the bulk we wanted to put the source.
Any other comments? Okay, let's thank Mukund again.